ProfessorDonaldRubin, who is the John L. Loeb Professor of Statistics at Harvard University. I typically introduce speakers by saying who they are and what they do, but there is no introduction really that would do justice to Rubin's record, so I will not call this an introduction. If I had to say it in one sentence, I would say he's one of the most influential statisticians of our time. That's the sentence I would choose. If I had to say in a few sentences, I could say he has made contributions in causal inference design and analysis of experiments, missing data and Bayesian analysis that have changed the way we think. That's in a longer sentence. And then I would just share a few facts with you about his biography. He's an elected fellow of the American Academy of Arts and Sciences, the American Association of the Editorial Examiners of Science, and the American Statistical Association, among others. He has honorary doctorates from several universities around the world. He has about 400 publications, give or take, including 10 books. And this is my favorite fact about Don Rubin. He's one of the most highly cited scientists in the world. And so as of today, I just checked, he had 166,921 citations. That is roughly, to give you an idea, 1.5 times the entire population of Cambridge, Massachusetts, and about 1.42 times the entire population of Ann Arbor. That's the entire population, including babies and private families. The yearly citation in 2013 was 16,000, which is a little bit less of the entire population of Ypsilanti. So his citation rate is about one small city a year, which I think just summarizes his influence. We are honored to have him be part of the ISQM series, and we're very grateful, Don, that you took the time to come to Ann Arbor and to travel and pay the cost, the timely cost of traveling. So because of Don's popularity, we have an unusually high number of attendants. The ISQM is usually popular, but not this popular. But I'm gonna take 2 minutes of your time and Don's time to tell you a little bit about the series, because I won't have this chance again. So Matthias Catania, who's Associate Professor of Economics, and myself, I'm Assistant Professor of Political Science. My name is Matthias. We started the seminar series back in 2013 in the fall. We had the support initially of the Economics Department, the Political Science Department, and also the Center for Political Studies. We also had the full support of QNP, QNISR, and we now have support from the National Science Foundation and the university as a whole. So we have a lot of funding sources and support from the university. The seminar was intended to build an interdisciplinary community in the university. It's focused on quantitative methodology. We have, the typical topics conceptual rather than technical, and we aim for the talk to be accessible to a broad and interdisciplinary audience. Our goal is to look at quantitative methodology from the perspective of many different disciplines and get scholars from all these disciplines talking to one another. And we run every other Wednesday at 4 p.m. You can find a website at, if you go to Google ISQM Michigan, then it will come up. It's the first entry, and everyone is welcome. We hope to see you in future talks. Future speakers include Bill Jacoby, Tyler Vanderbilt, Julia Pearl, Brian Graham, and others, so you can check it online. Then one word about the rules of the seminar. We usually follow what I call econ rules with a caveat. So the econ rules means that we can interrupt at any time and we can dispute and we can talk even about the title of the talk. The caveat is that we are nice to one another and we are respectful. I don't know if these rules will work today because we are a lot, so I will let Don decide how he wants to handle. We have an hour and a half. We go until 5:30, so I'll let Don handle that. He might prefer to talk and then open to Q&A. That's all I have to say. Don, again, thank you very much for coming. I'm taking the time to come talk to us.
Thanks so much for that overly gracious introduction. I should say, coming here, in a lot of ways, it's like coming home. Partially because I see so many friendly faces in the audience. I mean, there's one I've known for 4 decades, which is an amazing length of time. And there are other people I haven't known that long. But Susan, how long? 20 years or something like that? Two couple decades. And so obviously there are a lot of people here in Raghu, my former students, Ben. So it's great to see you all. And also, I have a family connection here because my father was one of 4 brothers, all of whom went to Michigan as undergraduates. And 3 of the 4 got law degrees here. So being here is also coming home for that reason. Probably the first time I was in Ann Arbor was before any of you were here. I remember driving up here from Chicago. I don't know, it was 1950, whatever it was, 8 or something. So it's great to be back here and feeling at home. So the topic for this talk is one that I thought was supposed to be stimulating of conversation, understanding concepts for causal inference in randomized experiments and observational studies. There's going to be sort of a lot of historical comments as well, which I think are useful, partially because I think many people who worry about causal inference in statistics and computer science and other fields aren't aware of the history. And so I make some historical comments I think are useful. So let's see, do I know how to use this thing? I guess I don't. Okay. Yes. So I started this talk with a prologue. Oh, with respect to Susan's comments, I don't mind being interrupted. So if people want to interrupt, do so. But I guess if it gets too many comments, then it'll get pushed. It'll become too lengthy, and then I'll let the chair decide whether we should shut it off. I mean, we're throwing it back and forth in each other's laps. But so this is a prologue to causal inference. I mean, my introduction to causal inference in science, in some sense, started when I was in high school. My high school wasn't that far from here. It was Evanston, Illinois Public School, and my big thing that I really loved was physics. And as an undergraduate, I went to Princeton in physics, and the professor there was this guy, John Wheeler, who was well known to some of you who know about physics. I think he's probably the most famous American physicist to never win the Nobel Prize. And there were a couple things that he is noted for. One, he was the PhD advisor for Richard Feynman, who was a very well-known guy. And the other thing he's noted for, according to Wikipedia, is that he invented the name black holes. And but he always denied that. But what he says is he was giving a lecture describing black holes, and somebody says, "That sounds like a black hole," from the audience. And so he picked it up, but he said he never made it up. He never found out who that person was. So he was a very stimulating professor, and really continued my interest in physics and the basic idea of there's something special about science. And basically the idea about science is something you want to learn about science, and then you do experimentation, you learn about it, you do more experimentation, you learn about it. There's always something that you don't know. When I went to graduate school, I didn't start out in statistics, but eventually I ended up in an experimental design course with Bill Cochran, who was my PhD advisor in 1968. And it's completely consistent, this idea of you do an experiment to find out what would have happened under different conditions, and then you learn about these recondite or missing values, and then you go on and you do some more experimentation. One of the very important messages from both my high school days and my days at Princeton in doing physics, and from Cochrane in 1968, is there was a clear separation, conceptual separation, between the science, the object of inference, which was based on defining questions first, and what is done to learn about the science. If you want to learn about the science, you intervene and do different things at different points in time. The fact that you can't measure everything doesn't mean that science didn't exist back then. It existed, but in order to learn about it, you have to intervene. So the science is this abstract thing that exists, and then you get to learn about it by doing experimentation of various different kinds. And in experimental design, classic experimental design from Cochrane is you do randomized experiments. That was the theme of that. But the point is you have the same notation, representation of the science, no matter how you try to learn about it. So the fact that you that here the science sort of exists, the planets exist in various places, and you try to learn about it, doesn't change the values back then. And the act of learning is a very different conceptual act than what existed. And I'm not saying that's true, and I'm certainly not saying that my understanding of science is completely accurate, but this is more for why I think about experimentation, causal effects the way I do. It was sort of a predicate for how I think about this. And so the important idea is that science that exists and the same notation and representation of it, no matter how we try to learn about it or measure it. The other important thing from this background in physics is that missing data always exist. You cannot go back in time and do another treatment. Time marches on. And there are different ways of describing it. One is time marches on, but also there are these principles from physics. One's called the Heisenberg uncertainty principle, which is quantum mechanics idea. Sometimes it's slightly confused with the observer effect, meaning that if I intervene in such a way that I want to measure momentum, I cannot, back at one point in time, I can't measure velocity at the same point in time. By measuring momentum, I disturb the system in some way and change the velocity. So I can't go back in time to make the other measurement. And so consequently, the idea that when you're doing experimentation and trying to learn about science, there's always going to be missing data. That's just part of the fact of life. That's the way it works. And so this idea that science exists at some point in time, but there are all sorts of values, and you can't learn about them all, and the act of learning about them is entirely different. What do I mean by the act of learning? Well, for example, if I do a randomized experiment on postmenopausal women to learn about the effects of hormone replacement therapy, the idea is that if I gave this group of women hormone replacement therapy or not, and I watched their outcomes, how I learned about it doesn't change the outcomes there would be. So if in fact it would, meaning that if I learned about these through an observational study or through a randomized experiment or through observing people coming out of a doctor's office, there'd be different effects. Then why am I doing the experiment? Why would I even like doing randomized experiments? I'm not saying it's true, but it's basically a tenet of this approach to science that I'm adhere to. Now, what are some of the really essential ideas of causal inference? Well, one of the most essential ones is actually due to Fisher in 1925, that you should actually assign treatments to units randomly, and that allows you to learn about science. It's an essential idea. And what that does is thereby creates balance on covariates, background covariates, and expectation between treatment group and control group, or many treatment groups and each other. And what if you got a bad randomization? Well, one of the pieces of advice from Fisher that's basically recondite, sort of hidden, is that you should re-randomize. You should not live with a bad randomization. And there are many sort of religious advocates of randomization-based inference that wouldn't agree with that, although I believe that Fisher was exactly right. I found out about this when I asked Cochrane the question, what would you do if you got a bad randomization? Should you re-randomize? Or should you live with the bad randomization? Because that's what the asymptotic t-tests and f-tests tell you should do. And Cochrane was unequivocal, saying, I asked Fisher that once, and Fisher was absolutely clear you should re-randomize. You don't want to live with a bad answer. And if it screws up the asymptotics, it screws up the asymptotics. Yes?
Can you tell if it's a bad randomization?
Well, the question is, well, how can you tell whether it's a bad randomization? Well, if I'm doing an experiment with, for example, 2 treatments, one a placebo, one an active treatment, and I have 100 patients, 50 males and 50 women, and all the women get the active treatment, all the males get the control treatment. That's a bad randomization. Even though in expectation, they'll be half and half. Not slightly, but yeah, badly.
49, quick question. It's not a question, how do I tell, right? If I pick some
I thought that was your question. How can you tell?
That's an example, it doesn't tell me how. The issue is exactly 100%, then, okay. But is there a, when you focus on observables, not unobservables, randomization is balance everything.
Mhm.
And I thought randomization is, you can't really tell randomization is, but it's about the process that you use.
Randomization is about the process you use, but the objective is to get balance on observed things as well as unobserved things. And you can't do anything about unobserved things, although many economists would like to. What you can do is make sure that on the observed things you will not get a bad answer. And in fact, you can do the whole theory of randomization and p-values and unbiased estimates works with re-randomization. It's just that the usual asymptotic test statistics don't. And I think if you read carefully, the older guys like Fisher, Box, Cochran, that they knew that, but they couldn't compute anything. They didn't have computers, so they couldn't do re-randomization tests. Because the effort to make these re-randomization tests work, you have to, and when you're calculating p-values, do all the re-randomizations again in order to get the right p-values. There's an article that's published in the Annals of Statistics about 2 or 3 years ago with a former PhD student of mine, Kerry Locke Morgan, who's now at Penn State, where we show this. And actually, it's an interesting article also because we go into some of the history of it and have quotations from upon why that's the right thing to do. And it's only the wrong thing to do if you're in love with asymptotic tests. You can do everything closed form. And the old guys knew that, but they couldn't compute the right tests. So that's why they advocated the wrong tests. Actually, I think that's going to be a theme that's going to re-rise. I really appreciate that the question because it's a theme that's going to repeat itself here. That a lot of the things that we're stuck doing, the old guys knew that they weren't really the right things to do, but you couldn't do the right things because you couldn't compute. And so we're stuck with the baggage of the past, and some of the baggage is doing really kind of stupid things because we could compute them. But if you read more carefully, they knew that those things weren't the right things to do if you could compute things. But would you ever think of proposing something that you couldn't possibly do in 1935 because no one would ever do it? So you wrote about things that you could do, not things that no one can do. And so this idea of re-randomizing, you can find that in Fisher. It's kind of hard to find. But then in order to assess this Fisher-Nell hypothesis of no treatment effects, is basically a stochastic proof by contradiction. You only re-randomize over the acceptable randomizations. So when you're calculating p-values, you don't re-randomize over all possible randomizations that you would have rejected. And that's how you get the right answer. And that, if you read Fisher carefully, you can see that was the advice. And I view these Fisher tests as a special case of something that I call posterior predictive p-values in a paper I wrote in the Annals of Statistics in 1984. And I think that there are wonderful Bayesian generalizations of these Fisher randomization tests that if incredibly demanding computationally, but they dominate classical methods, like for selecting active from inactive effects in multifactorial experiments. They actually they dominate, from a completely frequentist point of view, the traditionally accepted methods, because they build in the uncertainty of parameter estimation and posterior estimation of missing values. Now, one thing that's interesting to me is that Fisher obviously understood this idea of causal inference being a missing data problem. You can't go back in time to give the other treatment. And why do I say that? Well, here's a quote from Fisher in 1918. I don't remember the place right now. That if we say this boy has grown tall because he has been well fed, so that's the active treatment in some sense, he's been well fed, we are not merely tracing out cause and effect in the individual instance. We are suggesting, this is sort of the bungled Old English writing, we are suggesting that he might quite probably have been worse fed. Rod, you can interpret that, I can't. It might quite probably, I don't know, very subjunctive, which English and Scottish seem to love. It might quite probably have been worse fed. In that case, he would have been shorter. So under the controlled treatment, he would have been short. Under the active treatment, where we see he's tall, so therefore the causal effect of being better fed is he's tall. Obviously understands that idea. But remarkably, Fisher had no notation for these scientific concepts. He never wrote any notation for this at all. So that despite having these wonderful insights about randomization and actually proposing randomization, and active randomization, he never wrote down the notation in the general case. Actually, it's interesting to go back and read the literature between like 1920 and 1923. There are other people who talked about if we had randomized the plots. Gossip, student, wrote things like that. So sort of randomization was in the air at that time. But people talked about it as a mathematical property. Fisher was the first to actually propose physically randomizing doing what the mathematics told you to do. And it's not the first example in science where somebody had sort of breakthroughs because they looked at what the mathematics was saying and actually saying, gee, the mathematics is saying something deeper than just the mathematics. And one of the examples was Einstein looking at Lorentz equations. Why was he doing that? How did he have he was working in the Swiss patent office, right? What was he working on? How did relativity come up? Well, he's working on coordinating the clocks at the train stations so they'd all go click at the exact same time. And how do you do that? If you're in Bern and Basel, how do you make sure that both clocks go at the same time? And the problem is that how do you communicate? There's a time of communication. That's what led to the special theory of relativity. He was trying to solve an applied problem. He wasn't looking at patents for stamps or something like that. How do you lick stamps? He was actually trying to solve this real problem. It had to do with the time of transmission. And other people looked at Lorentz equations before him, but he took the mathematics seriously. So this is not to denigrate in any way Fisher's insights. I mean, he had tremendous geometric insight under this Fisher-Null hypothesis, which implied all these asymptotic tests based on spherical distributions. Great stuff, but the point is he never had notation for these causal effects as described in this particular quote, for example. He obviously had the idea, but he never had notation for it. Where the notation is another essential idea of causal inference. This idea of potential outcomes, meaning that there's one outcome you would observe under an active treatment, another outcome you observe in a controlled treatment, is due to Neyman in 1923, and his thesis was written in Polish. So it never really got fully translated until 1990, amazingly enough. But what he did is he defined quantities of interest to estimate, estimands, in randomized experiments as function of these potential outcomes. Explicit notation for that. So let's suppose y is the outcome variable, y0 is the array of potential outcomes under a controlled treatment, and y1 is an array of potential outcomes under some active treatment. And he implicitly assumed an assumption that I call stable unit treatment value assumption, STUVA, which I write about in the 78 Annals paper and a 1980 JASA discussion. The point is, but this was Neyman's insight in doing this notation. You can't observe both outcomes on any one unit, any one plot of land, he was talking about, at the same point in time. This plot could either expose the active fertilizer or the controlled fertilizer. And you can only observe one of them, but what you want to do is you want to compare what would have happened if they'd all been exposed to the active fertilizer, they'd all been exposed to the controlled fertilizer. So that's it's an essential concept that the estimands are comparisons of potential outcomes, only one of which you can observe at best. And you can only observe that under other assumptions. You can't do causal inference without making assumptions. And that's an essential idea. And then Neyman also had that you should evaluate the operating characteristics of procedures over the randomization distribution. And this is what led to our t-tests, asymptotic confidence intervals, frankly, f-tests. There's an interesting history comparing Neyman and Fisher fighting about f-tests in Latin squares, where they're both wrong, and which is an amazing fact. When you go back to this 1934 paper, they're bitching at each other, and basically they're both wrong. And that wasn't, and part of the problem there has to do with the computation. The algebra was incredibly tedious, even in a simple setting. And in order to verify the algebra, it really helped to be able to do simulations. And the fact that they're both wrong in general, I finally found a graduate student who was interested enough in pursuing that, and that's now published in Statistical Science maybe a year ago or something. Armand Sabati, who's now at Purdue. And we show that they're both wrong in general. I mean, in very simple ways. And Neyman was relying on his students to do the calculations. Fisher was really relying on his hostility to say why Neyman was wrong. Saying, you know, basically at one point in this discussion, he says something like, I wished when we invited our foreign visitor to visit us from the continent, this is 1935, or I think it's 35, to give a talk at the Royal Statistical Society, we had all hoped that he would talk something about which he knew. However, he decided rather unwisely to talk about something about which he is completely ignorant. And it goes on like that. It gets worse. And one of the important contributions of this notation in this paper by Neyman in 1923, he talks at great length about the role of non-additive unit level treatment effects. There's the treatment minus control difference. If it's not the same for every unit, it's called non-additive, back in the terminology of that era. And which you have non-additive causal effects, that means the treatment effect varies from unit to unit. Or the other way of saying it, there's a non-zero correlation between the potential outcomes. Under Fisher's null hypothesis, there's nothing going on, so they're automatically additive. And Fisher was kind of peeved that Neyman would think to question this. And basically, he goes on to say something like, you know, it may not be, this role of additive effects may not be the right thing to test, but I wish Professor Neyman every luck in inventing a form of inference that's as successful for his hypothesis as my form of inference is for mine. Basically, go away. I did something great. And the thing about this is it's true that this non-zero correlation between these potential outcomes that you can't estimate directly, but it alters the inference. And it alters the inference in such a way that it bothered Neyman in 1923 because he had this asymptotic confidence interval that did not have the right coverage. Basically, it could have had too much coverage. Didn't call it a confidence interval. He called it, you know, interval based on normal asymptotics. But you can show that in general, with a non-zero correlation between the potential outcomes, it had overcoverage in expectation because the width of the interval was too big. Bothered Neyman in 1923. He got around that in 1934 by defining a confidence interval to have at least its nominal coverage. And that's what a confidence interval is. Not the exact coverage, but at least its nominal coverage. And that's the current definition. He just defined it away mathematically. Not very acceptable, and Fisher bitched at him about that too in 1934. There's this other thing that has sometimes been called Rubin's causal model that just tries to generalize the stuff to more general settings beyond randomized experiments. And the remarkable thing is, if you look up until maybe 1974, everybody in non-randomized settings defined causal estimates as regression coefficients or something else. They didn't define those in terms of potential outcomes, despite the fact that Neyman used these potential outcomes in 1923 And they became pretty standard in experiments to use it that way. If you read the old textbooks like Kempthorne, he used potential outcomes all the time, but in the context of randomized experiments. I once visited Berkeley in the 70s, and I was on this kick that potential outcomes define causal estimands in all situations, randomized experiments. In this time I visited Berkeley, I had an office next to Neyman, and he'd retired by then, but he disagreed with this. He basically said it's too speculative to talk about potential outcomes unless there's an actual physical probability distribution that you can control to reveal them. He said, no, I don't want to talk about that. I don't want to talk about epidemiology. I don't want to talk about noncompliance. I don't want to talk about any of these things. It's too speculative. Instead, he said, let's talk about astronomy. So we talked about astronomy. Another, I think, contribution of looking at potential outcomes as defining causal estimates in all situations is that you can define an assignment mechanism that's needed for causal inference. This is a mechanism, probability mechanism, that defines the probability of treatment assignment indicators, W, given the science. So it's a probability of the treatment indicators, zeros and ones, given covariates, X, which could be blocking factors, and the potential outcomes, which is kind of a funny expression when you think about it, because it's something you're going to do now in some sense, assign treatments as a function of things that you observe, blocking factors or covariates, and something that you can't observe until the future. So people used to object to that, and that's, I think, one of the reasons Neyman objected to this idea. But it has the virtue that you can actually state the benefit of randomization. And if you look at the literature until these papers, you could talk about the benefit of randomization, and talk about unbiasedness and other stuff, but you couldn't state it mathematically. What does randomization do? And the very simple statement is it creates assignment mechanisms that are unconfounded. In other words, that the probability distribution of the treatment indicator can't involve the potential outcomes. It just depends upon covariates that you can observe. So I think it's another advance, and in some ways, it's remarkable that nobody noticed that before. But you can look in all the literature, and I've looked very hard to find another. I don't think there is anything there. An ignorable treatment assignment it's one where it depends only on observed values of the outcomes. That occurs in sequential designs, where you're playing the winner. So it can depend upon what you observe. It can't depend upon what you're missing. Because anything that for any unit for which you haven't assigned a treatment, that value is missing. And so that's what randomization buys you, in some sense. Even in a sequential design, it buys you that it's ignorable. And y-obs here are the observed values of the potential outcomes. Bayesian, and this also embeds Bayesian inference within the classical, because what Bayesian inference says is you have a model for the assignment mechanism, treatment indicator given covariates and outcomes, and Bayes just models the science. You put a model on the random variables that we typically call the science, covariates and outcome variables. And this again emphasizes, do not model the science and how you learn about the science. The science is this distribution, or these values. Neyman consider them fixed, unobserved values, but that's the science. And then this assignment mechanism is what you do to learn about the science. Two completely separate activities, two completely separate, distinct conceptualizations of what you're trying to do. And do not model science and learning about the science. It's, I think, an incredibly important lesson, and basically misunderstood for a long period of time. So here's the potential outcomes approach to causal inference, the simplest setting for the science under the stable unit treatment value assumption. Basically, rows are units. Y1 refer to the potential outcomes if everybody got assigned the active treatment, and Y0 are the potential outcomes if everybody got assigned the control treatment. And you can define estimands, for example, the average causal effect, the average Y1 minus the average Y0. Or you can define the median causal effect, the median of the individual causal effects. Or it could be the median of the Y1s minus the median of the Y0s, different in general. But the point is that all the estimands, all the quantities, are functions of the potential outcomes, of Neyman's potential outcomes. And under Fisher's, no, what Fisher was saying is the two columns are identical for all the units. And additive effects are just saying the difference between y1 and y0 is constant for all the units. And although this is sort of, in some sense, baby stuff, it's incredibly important. And it's pretty much was lost for generations. Obviously, the fundamental problem facing causal inference is for each unit, we can only observe y1 or y0. So pictorially, the first 3 units here got the active treatment. The next 3 units got the control treatment. And so therefore, you can only observe at most half the data, half the science that you want to see. And so what does randomization do? Well, randomization takes a random assignment of active versus control, takes a representative sample of the y1s, will be compared to a representative sample of y0s. It's sort of obvious, isn't it? It's obvious that randomization does that. And a representative sample should represent the whole column vector. So why is that not obvious? It is obvious in some sense. But why did it take thousands and thousands of years for somebody to propose doing that? The Greeks didn't know it. The philosophers didn't know it. Mills didn't know it. John Stuart Mill, he didn't know it. But my view, if you read the philosophers, they're totally confused. The people who came closest were the people who did experiments. But they still didn't get to this point that if you take a representative test, why is it so tough? Well, you had to use potential outcomes to represent it. If you weren't using potential outcomes, you just represented the observed values, nothing's missing. So you're not taking a representative sample of anything, so there's nowhere to go. I've looked very, very hard for where these ideas came from. And there's an American philosopher of psychology named Peirce. That's how you pronounce this weird name. In the 1880s, wrote stuff about how if you take haphazard samples, you sort of represent the whole column. Very interesting guy, who actually did randomization in experiments, not for inference, but in a psychophysical experiment so people couldn't get the next thing. As I said earlier, Gossett had phrases, Fisher had phrases, but why did it take so long to realize this completely obvious fact? There are only 2 things. One, you have to think of it as potential outcomes. And you have to think of a haphazard or random sample of a set of values can be used to represent the whole column. Whether you want to estimate the median or the mean, doesn't make any difference. Any function works. Why did it take so long to, I don't know. Except it's obviously not obvious. So you can think, now it's completely obvious if you phrase it the right way, but obviously it wasn't obvious for thousands of years. Why? Well, here's an example. I don't think we were wired to be very good at assessing uncertainty. And I just call this example Hunter's paradox. I'm sure that there are other ways of saying this better. But basically it's an example where sloppier statistical thinking could lead to more success than misapplied careful thinking. This genetically. We're not wired to do this right. So let's suppose we're talking about 2 tribes or something like that, and are hunting in Europe or something, and thousands of years ago. And suppose going north to hunt was more successful than going south. So you ate well 60% of the time if you went north. You ate well 40% of the time going south. Now, a data gathering tribe, data miners or something, noticed this and subsequently said, we should go north 60% of the time and south 40% of the time. And the data ignoring tribe never noticed this information. They didn't collect data and decided to go north 100% of the time. Which tribe ate better? The data ignoring tribe or the data gathering tribe? The data ignoring tribe, because they ate well 60% of the time. Whereas the data gathering tribe ate well 0.6 times, I'm assuming randomly, 0.6 times 0.6 with 0.4 times 0.4. So there's not much empirical support for thinking carefully. Of course, what this shows is that you have to have a big framework that not only has science and learning and decisions, you have to use loss functions. So the 0-1 loss that's what all data miners use. They get the right science? No, they'd say they don't get the right science. They eat better, but they don't get the right scientific You know, this is, I'm talking now to people who do cross-validation. This is basic cross-validation. That's all it is. Cross-validation does not get the right answer for science. If you get the right answer for science and you add the right loss function, then you get the right answer. So this is my criticism of data mining, guys. Okay. And instead what happened is after the early days of experimental design, people started taking OLS, ordinary least squares, very seriously, and all its companions. What do I mean by its companions? Like logistic regression, things like that. And they lost the potential outcomes and these key Fisher-Neyman concepts, and they went to this, what I call the observed value notation. So the observed value for the first unit, for example, or the ith unit, is an indicator, the indicator for what treatment he got times y1, the indicator for getting the control treatment times y0. So what is this quantity? Well, it mixes up the science, y's, with what you did to learn about the science. So it violates this basic principle that you should keep them separate. Because one's doing one thing and one's doing something else. It just mixes both of them up. So is yi obs a scientific quantity or not? It's not. It's not a scientific quantity. Is it a quantity that has to do with the assignment mechanism? No. What it does, in my mind, is it suppresses the key insights that causal inference is a missing data problem, and you're not dealing with the missing data. And I believe it's a retreat to confusion. Yet in the 20s, 30s, 40s, 50s, 60s, 70s, through the 2000s, it became standard notation in biostatistics, economics, epidemiology, everywhere. That's what everybody was doing. They reduced everything to the observed value notation. And even great statisticians, and I include Fisher and Cochrane, and a guy named Jerry Kornfield, who's probably the most active epidemiologist to be on the bandwagon cigarette smoking, confuse themselves using this OLS notation, the ordinary least squares with the yi obs notation, because you can't get the right answer doing that. And why is this OLS style so bad? Well, it buried crucial issues like this. If you're just using yi obs, how do you realize that the role of additivity of a constant treatment effect is important? It's gone. You don't see it. You reduce these two potential outcomes to the observed value. So you've lost the role of additivity, and you've lost the formal benefit of randomization. You can't even state it in terms of yi obs. If you try to state it in a way that's parallel to this ignorability, you basically end up with the conclusion that it only makes sense under the null, that there's nothing going on. Because otherwise, you're going to find yi obs is correlated with the indicator variable. So under everything except under Fisher null. So the inherent missing data issue is lost using just yi obs, and there's no longer any need to impute yi miss, the missing values. As a result, the estimands, the quantities of interest to be estimated, must be parameters in some model. They must be parameters, because that's the only thing that you don't have. If you have no missing data, the only thing you don't know are the parameters. So therefore, the estimands must be parameters in like regression parameters or logistic regression parameters or something else. And this led to what I regard as asymptotic silliness and sloppy mathematics. Because this distinction between finite population estimands and superpopulation estimands completely lost. Whereas the old guys, in their notation, they explicitly could say the difference between the treatment effect for the people in the experiment and the treatment effect for some superpopulation from which the units in the experiment were randomly sampled. They didn't even know how to generalize beyond the superpopulation. And this led to an emphasis on analysis methods and estimators rather than estimands in study design. So they lost the emphasis from this old literature on what are the quantities you want to estimate and how do you design a study to estimate them. Instead, the whole focus became, I got a data set somewhere, here are the things that I've observed, now I'm going to put down regression models and figure everything out. Which I think is completely wrong to do it. And yes?
So when did in physics did they start to separate the science from learning about the science? About when did this occur?
My understanding, it was in the early 20th century.
So in a way, this whole way mean, at least
Yeah.
it stems from that. It was waiting for those guys.
I think
to
that's
make
right. Although I don't think they talk to each other that much. But I think it was sort of one of these things that's in the air. Maybe they were taking, physics courses when they were at Cambridge University or something like that. This is the way you think about it. And they didn't take philosophy courses, thank God. They would have gotten confused. And so one of the questions, why did the OLS style, the ordinary least square style, become so dominant? And I think that because these old guys understood the issues, it has to get with computational limitations in the past. You couldn't do randomization tests. You couldn't do evaluations of name and operating characteristics of procedures in small samples or under various alternative assumptions. Because that required simulation. Nobody could do simulation back then. And people started using mindless off-the-shelf batch programs. It became standard and acceptable in publications. And you look at many articles, my experiences, publications are acceptable if they use the same method that was used before, no matter how stupid it is. And so instead of describing what their hypothetical experiment is, they'll tell you what program they used. I use SAS Procmix 3.0. What the hell does that mean? I don't know. So, and people who understood these issues in randomized experiments tended to avoid observational studies. I think along the lines of the Neyman quote, it was too speculative. And they didn't do that, and they returned to the comfort of randomized experiments. They never dealt with these non-randomized experiments, epidemiological experiments, although they knew the difference. And that generation largely passed, they're gone. I think a lot of these guys who really did understand the difference. I mean, George Box, died last year at 91. David Cox just turned 90, I think. Herman Chernoff is 91. Chernoff never did much on experimental design, but he understood the issues. And instead, it was left to epidemiologists who are basically dealing with really important problems, but they're trained in medicine, mainly. We're left to try to figure this out. So my idea is, so these don't fall into this trap of losing sight of these historical breakthroughs that I think occurred in the 20th century. Leading to randomized experiments. And so I think that the terrible influence on the way observational studies were treated. Association versus causation was completely muddled. Because if you just look at regression equations, that's all you're looking at is causation, is association. And yet these words of warning, association is not causation. What is it then? What's the difference? Because a key example is what I call case, non-case studies, case control studies, where the outcome variable, YI-OBS, are you diseased or not? And the treatment indicator is, did you get, let's say, vaccinated or not? They're both dichotomous. So putting them in a model works either way. You can do a logistic regression of YI-OBS, the observed value of diseased or not, on treatment indicator, or you can do a regression of a treatment indicator on YI-OBS. And the relative risk is going to be the same. The risk, relative risk. So logistic regression works either way. But what does YI miss? It's lost. When you do it, it's just not in the equation because you've switched all the data to YI-OBS. And so this idea of the sampling of an assignment mechanism, which is how you got assigned treatment, is lost. And the sampling mechanism is which units do you include in the sample? That's lost too. We haven't really talked about the sampling mechanism, but in these case control studies, sampling mechanism, for example, in a surveillance system, samples all of the cases and a random sample at best of the non-cases, of the people who don't have the disease. So you're explicitly choosing things to look at that are based on what they would have been under the treatment they got. So the sampling mechanism is confounded. It doesn't work right, in general. You can find special forms where it works right, but this is a quote from Cornfield in 1959 that I sort of like. It's a great article in general. As I said, Cornfield was a great epidemiologist, worked at the National Cancer Institute. We now consider the distinction between the kinds of inferences that can be supported by observational studies, whether prospective means you collect the background information and then you look to collect the outcome data, or retrospective. these case control studies, where you look at cases and non-cases, and then go back and try to get the covariance values. So supported by observational studies, and those that can be supported by experimental studies. Obviously, by experimental studies, it's clear if you read it, it's talking about randomized experiments. That there is a distinction seems undeniable, but its exact nature is elusive. What was it? Is it really that elusive? This thing that generally depends upon potential outcomes doesn't. Is that elusive? No. It's right there. But if you only had words to describe this, and you reduce everything to yi-obs, the observed value, you can't even state it. So it is elusive without having the right notation. And this guy was absolutely no fool at all. Yeah.
In this era of computerized everything,
Yep.
when we have ecological monitoring, data collection through, let's say, accelerometers, and we have randomized our sample already, how can we include the people that decide to take the accelerometer off into our data? They are our missing. They were already randomized into the study, but they took the accelerometer out. We don't have the data.
Yeah. Okay. So you're talking about. Right. Well, here in this talk, the why I miss only refers to the missing values due to the assignment mechanism, the potential outcome. Now, dealing with missing data, in addition to that, which has to, so if they take the accelerator off, for example, so you can't collect data for them, that's a missing data problem, and there you have to worry about how the people who take them off differ from the people who leave them on, and whether, in fact, taking them off is altered by the treatment that they got. Because taking it off or leaving it on is in principle, an outcome variable. And as an outcome variable, can be affected by what treatment is somebody. There are ways of dealing with it, but it's certainly beyond what I'm talking about here. Yeah.
So in education, we have now about 10 studies that show randomized observational studies with pretest can closely approximate the results of randomized experiments. So I'm curious how you respond to that and what role the pretest is playing in this logic.
Right. Well, basically what these are examples where if the pretest is good enough, then you can believe that the assignment mechanism, whatever it is well explained by those covariates. It has nothing to do with those covariates explaining all the outcomes. That's one of the things that's befuddled in the thing. You'll never understand what nature is doing or God is doing, why some people fail, why some people succeed, why some people die. That's trying to model the science. But you can pretty much often decide why some people got assigned the active treatment, why some people got the control treatment. So in medical trials, doctors look at records. You know what the records are. May not know how they look at interactions, but in general, modeling the assignment mechanism is not as difficult as modeling the science. Because we pretty much know what people do. Not always, but I think that in many educational studies, I think we pretty much understand why people take one treatment or another, get exposed to one or the other. And that's the game we have to play, because eventually we're going to have to make an assumption about this assignment mechanism, and then try to adjust for the variables that affect the assignment mechanism. And that gets to the next point in some sense. So how do we deal with observational studies? I think what we really have to do is try to design observational studies to approximate randomized trials. And the first issue here is to basically hide the outcome data until the design phase is complete. Meaning, if you have a data set where you have an outcome variable and you have treatment indicators and covariates, get rid of the outcome data. Because you can never, in a randomized experiment, you never get to see the outcome data until the study's over. You want to do, for the same reason, you do that, to maintain the objectivity in an observational study, try to approximate a randomized trial as closely as possible. Hide the outcome data, then think very carefully about the the decision makers, and the key covariates that the decision makers use to make treatment decisions. If you do that well, then you have a chance of getting the right answer. If you have a data set where these key covariates are not observed or very noisy, it's usually best to give up and seek a better data source. So don't beat a data set to death looking for an answer. Sometimes it's the only data set you have, and then go ahead and analyze it. And then if you do have these key covariates measured, you're confident of that, then try to find subgroups, subclasses, or matched pairs in which the treatment and control groups have balance, essentially the same distribution of observed covariates. And you have to admit it's not always possible to achieve balance. And then inferences are limited to subgroups where balance is achieved. You may have to throw out people in one treatment group who have no representatives in the other treatment group. And as you know, it's a very strong theme of randomized experiments is that it's better to have the right answer for some subgroup of people than so a bad answer for a larger group. Because the act of generalizing to a larger target population is a different activity than getting the right answer somewhere. And so if you have such a situation where you have a subgroup of people well defined, then you should do a protocol. Before you look at the outcome data, you should specify how you're going to analyze the outcome data. This for an observational study as well as a randomized experiment. I mean, as we all know who've done anything with FDA, Food and Drug Administration, you have to specify primary and secondary and tertiary analysis before you look at the outcome data. You can't start changing the definition of the outcome data or the analyses after you look at the answers. But in observational studies, that's the norm. People just start analyzing the data, doing regressions, logistic regressions, least squares regressions, putting in different predictive variables. And academics certainly are not free from bias in such situations. In fact, maybe they're more susceptible than even companies because academics get prestige, get promoted based on publications. A publication that shows nothing is not likely to get published. An article that shows nothing shows nothing. Why should I publish it? And so academics are equally sensitive to this criticism that they're just mining the data to get something significant. But I think if we follow 1 through 5 in an observational study, we have a chance to create an objective design that approximates a randomized trial in each subclass that is balanced with respect to observed covariance. And that's a long way of actually answering your question, too, saying I think people are getting much better at doing this. At least in my experience with people at NPR, for example, Chauchet, they're aware of this when they look at observational data. That this game of keeping the analysis blind to what the answer is until you've designed it and specified a protocol is the right thing to do. It doesn't guarantee you're going to get the right answer, but at least you have a chance of getting an objective answer.
So political scientists, for example, often have unique data sets, say historical data sets, or very expensive, at least for political science data to gather. And they're really interested in, say, the election that happened last time or something like that. My understanding of the advice would be if your indicators are noisy and all that, the data is there, get a new data set. Okay. Well, we can't do that because of different reasons. I assume the advice is you can't really do causal analysis in a reliable way, or trustworthy way, or believable way in experiments. And so just give up on the idea of trying to extract the causality from data that have not been designed actually. They just came up there, the world. And that also may be that in general it's not possible to do causal analysis backwards because this is very much a prospective kind of thing. Do your design and get your data and everything. The political science course is a big revolution using the Rubin causal model in its various forms to look at all kinds of data regardless of where it comes from. Do you have an opinion?
Yeah, well, the way you stated it, it basically says that if you had to follow this this specification, you'd close down all political science departments because they can't do anything useful.
No, some do experiments.
Right? Yeah. So yeah. And that's obviously pushing it farther than I want to push it. This is an ideal way to do it, to do science from observational studies, and I think that you should push that way. So if his example was an election that took place in the past, the outcome is probably the outcome of the election, Democrats versus Republicans, and you have a bunch of covariates for districts describing background characteristics, racial characteristics. Pardon? Right. Right. Yeah. Yeah. It's observation data. You see what you get, and so if the and the treatment here is what, whether the district is more Republican or more Democrat, something like that. Okay, and so you divide the units into Democratic units, or we'll call treated, Republican units, which are called control. Then you have a bunch of covariates that you're going to believe are pre-treatment versus control. So that means they took their values before the district became Democrat or Republican. Sounds kind of absurd, but if you want to do that, state it. Don't bury it in the proc mix. I use this program, and therefore, reader, use your imagination. Come on. So you want to say that? Okay, that the racial composition of these districts preceded the assignment of their being Democrat or Republican. If you want me to believe that, state it. And then go ahead and say what all these assumptions are. And then go forward and say this is what you're going to assume. And as long as you state what underlies the analysis you're doing, I'm not going to say it's wrong, because you've stated the assumptions under which the conclusion is right. But you have to try to make some argument that what you're telling me to assume is plausible. Or say, this is completely implausible, but I got to get tenure. And that's a reason. That's why you're writing it. But I don't mind any analysis being done that's honest. And so as long as you're honest about what you're making me assume about these key covariates that are determining whether the districts are Republican or not, okay? And then you specify the analysis that way, okay? I wouldn't have much faith in what you're doing, because I don't know how you're going to leave these background characteristics the same for these districts and then change whether they're Democrat or Republican. What intervention would do that? So I think it's your obligation as a political scientist describing this intervention. Say, what the hell are you talking about? What intervention are you imagining? And if you don't describe it, what you're saying is no matter how you change the districts, change their political affiliation, the answer would be the same. Why should I believe that? So basically I'm saying that in most of those situations, I don't know what you're talking about. I don't know how to formulate it correctly. And he's leaving because he cannot stand this. No, he warned me before that he's going to have to leave. That's not really true. No, it is true. So again, I don't mind doing those analyses like that, but I want you to be explicit about what you're asking me to believe. And if you can't do that as a thoughtful writer, then why should you expect me to do it as an unthoughtful reader? The obligation is on you to make an argument, not to do some regression. That's my response. Key design tool, I think it's estimated propensity scores. That's now becoming actually relatively standard. Rod and I were just in D.C. Last week where we met with some people in neurosurgery who want to try to do observational studies rather than randomized trials in neurosurgery to some extent, because it's and one of the key ideas here, I'll skip to the last line, that I think that this idea of writing a protocol for the analysis of the outcome data before looking at the outcome data is important, because what you want to be able to do is create these subgroups with buy-in from all the stakeholders. I'm thinking now of a study that I was involved in for years at CDC with Division of Reproductive Health on in vitro fertilization. So with couples that are trying to get pregnant, how many, and they have 3 or more embryos to possibly implant, how many embryos should you implant? Should one freeze the rest, 2 freeze the rest? And there are advocates of both perspectives. And before you break the blind to the outcome data, You should have people look at the covariates and the balance that you have in the study and what the protocol is, and have both sides buy into it. Say, okay, advocates of implanting 2 embryos, advocates of saying 1 embryos. Look, as far as we can tell, you balance on all the important covariates that we think are available. And basically, I'll believe the answer, although I may not fully believe it, but I'll buy that you've done the best you can do with the data set that you have. At that point, you unblind the outcome data, and if there's an answer that comes forward, people are kind of committed to believing the answer. It may not be the right answer, but at least it's hard to back out and say, oh, I don't like that, you forgot to adjust for the log of the square root of age. Okay? Or something like that. So these ideas aren't really new to observational studies. In fact, all they're trying to do is borrow critical ideas from randomized experiments. Analysis of causal effects. Define the questions first, then define the science of the estimands. Ideally, you'd multiply impute the missing potential outcomes. I'm very Bayesian that way. That's what you should be doing. And there's a role for modern computational tools here too, because these are nonlinear relationships in general. So you want to use modern computational tools like splines and all sorts of other things. That's fine. And when parsimonious models are the goal, I think that there are ways to select parsimonious models. I'm a fan of using principal stratification ideas, but I don't want to say any more about that here. I just want to go to the final slide, which says you should distinguish carefully between causal estimation and conditional association estimation. So I think that perhaps some of the examples that you're talking about are really better thought of as conditional associations. I want to know the conditional association between whether a district is Republican and Democratic after I've created balance on the percent minority, the number of years it's been in existence or something else. And is that those can be interesting questions, but they're all descriptive. You're not actually proposing to intervene in some particular way. You say, this is just a fact of life. And we compare these things just without any conditioning on any covariates, this happens. When we condition on some covariates, you get a different answer. It shifts around. Those can be interesting. But to embellish them with causal statements implies that there's an intervention you're thinking about. And without telling you about the intervention, I have no idea what you're doing. So I think that a lot of these just should be switched to this conditional association. So because causal statements have implications for interventions, conditional associations do not, at least not without great care. And I think we should not conceptually muddle them. I've looked hard when they first got muddled in statistics and economics and people doing regressions. And I think, as far as I can tell, we can blame it on Udny-Yule in 1898 in the Journal of the Royal Statistical Society, where it's a decent paper talking about the mathematics of ordinary least squares and correlations and partial correlations and partial regression coefficients. But he started talking about causal effects. And here the betas were causal effects. Nothing to do with causal effect. He just related, what are the outcomes here? Like divorce rates or something like that as a function of the wheat imported from China. I don't know. Some crazy thing. And he's just doing regression. But the terminology, causal effects, started to be confused with betas, going at least as far back as that. And so my attitude is, do not return to past confusion, because there's a lot of it. But do retain the critical insights from the past. Yes, question.
I think conditional association, that's very persuasive. What would be your view about, once you have that, offering limitations acknowledged, some sort of informed speculation about, it seems plausible, maybe even persuasive, but at least plausible, for the causal story that is going on, which this invites us to, about which this invites us to reflect, would be the following. And then you do tell a causal story under those conditions.
That's fine, as long as when you go into the causal story, you're telling me what intervention you're thinking about. Just say, well, because of these are conditional associations, we now think it's causal. Well, what do you mean by causal? So you say, okay, we should intervene. So in his example, you're going to leave all the background characteristics of the districts the same, but you're going to change their political affiliation. Well, I can imagine something. Maybe have a big campaign, but leave everybody the same pretty much, and have a big campaign where you spend zillions of dollars in districts to convert them from being Democrat to Republican or something like that. No, I noticed. That's why I picked it. But yeah,
So you are inviting your readers to join you in speculating about what of a causal nature might be going on, even though you're acknowledging all you have shown or presented is a conditional association.
that's fine. I have no problem, because again, it's being honest. And I think you should reserve causal for when you have something in mind that you might be proposing to intervene.
But I want you to say it's honest and it's useful.
That's, yeah, and it could be useful.
I don't like it, but at least it's honest.
Yeah, as long as it's honest, I've no problem. And it could be useful, right? You're not going to get me say it is useful. You make me a political scientist or something. And it could be useful. But in my own way is that don't go back to the past confusion. Do retain these critical insights from the past, and the critical insights, I think, are these essential ideas of causal inference that really grew out of, in the 20th century, from these sort of blasts of insight that Fisher, Neyman had, and the extensions to observational studies. Yes?
What's your view of the following practice, which is pretty common in development economics, certainly, but which has created, or it's led to a lot of controversy. And this is in the context of randomized studies, where you have a random segment of a treatment. You're estimating the causal effect of the treatment. But what's very commonly seen is to include control variables on the right-hand side for sort of baseline covariates that are observed before treatment. And this is often justified on the basis of, one, improving the precision of the treatment effect estimate, and secondly, correcting for any chance imbalances that may have existed between treatment and control groups.
And so you're saying that you're working in the context of a actual completely randomized experiment, for instance, and he's putting in honest covariates, there's real variables that attained their values before treatments were assigned, and you want to control for them to improve precision. And the way you described it is you're going to, quote, control for them by putting them in a linear model. If you want to create balance, you should try to create balance, because you can't do that. You can't put regressors in without looking at the outcome data. You can't do a regression without having an outcome variable. So why not try to do that at the beginning of the design phase? Create subgroups of units, of treated and control units that look similar to these, with respect to these covariates. Because many of these covariates, like age, are going to have nonlinear effects. Age often, younger people are healthy. Well, if they're really young, they're unhealthy. If they're really old, they're unhealthy. So these relationships like that can be very How about interactions? Well, you create that balance in design if you can do it, even in the observational study, and get buy-in from advocates of both sides before you break the blind and look at the outcome data. Then also as part of the protocol, certainly say, and as part of the analysis later, in addition to analyzing the data within these subclasses or subgroups or matched groups, I propose doing regression adjustments within subclasses. And there's a lot of evidence that regression adjustment, even simple linear adjustments where you fit different straight lines within each subclass, improves tremendously when you have nonlinear relationships. Or maybe fit splines, but put that in the protocol. And once the protocol is agreed on, then break the blind. So I'm not objecting to anything that you said. I'm just proposing that there's a way to do that in a more intelligent way than the usual, let's throw in a regression. Yeah.
It's a great advantage to have the notation for counterfactuals. But one problem I have with our current notation counterfactuals is that we assume there's a reality. Say, why I observe, why I'm missing, and a single value, and reality actually exists. But reality may not exist either because something respondent makes up on the spot, there's no measure of happiness or intelligence or political opinion until you ask there's no reality, or there's a lot of uncertainty over time. This occurs a lot in a longitudinal setting. A chance effect makes you have healthier or have wisdom, and that leads to another chance and compounds over time. So it's hard sometimes to think of one single realized value for the counterfactual. It sets a person on a path that's a lot of uncertainty, or really a wide range of uncertainty on the path to the ending point, especially in a longitudinal setting when we introduce T and a lot of uncertainties between beginning and end point. So I'm puzzled by our lack of apparatus to conceptualize the level of uncertainty, both at measurement level and also over time.
Well, a couple things. First of all, I'm very pleased you made that comment because I don't like the general use of the word counterfactual because I like English words that mean what they say. So if I'm doing a randomized experiment and I haven't made the assignment of treatments yet, but I'm contemplating the science, which of the values for the first unit is counterfactual? The observed value under treatment or the observed value under control? Which one is counterfactual? No, neither one's observed. I haven't assigned the treatment yet. So which one is counterfactual? Neither is. Counterfactual is an English meaning. Counterfactual, not factual. Right? That's what it means. So that's why potential outcomes is descriptive of the general perspective. It's potential outcomes, it's not counterfactual. When you're doing inference, after you've observed values, you say the inferential method has to deal with counterfactuals. But the approach isn't counterfactual. It's like saying the randomized experiments are counterfactual. Huh? Counterfactual is not factual. That's not right. So I prefer using language that's correct rather than language that's abusive of what's going on. The other point is, how do you conceptualize a potential outcome? Well, there's a value that would be observed. And I say there are lots of things that can influence that value. I'm not dealing with that. I'm dealing with whatever would be observed would be observed. Now, if you want to build some more complicated model and something else would be observed, you can do that. But think of in the experimental setting, if I gave you an active treatment, I would observe something. If I gave you a control treatment, I would observe something. And that whatever that's observed, that's the potential outcome that you're observing. It can be influenced by lots of things. You could have gotten hit by a bus after being randomly assigned. So, but the potential outcome you'd observe then is you got hit by a bus. You're dead.
But a lot of this notation assumes that the time of assignment outcome somehow is there to be reviewed. At least some of the teaching that you give. A lot of times people assume it's already will be there. It seems as if it's a fixed value to be reviewed by.
So, wait, you mean the potential outcome is a fixed value to be revealed? That's the attitude. That's right. That's what Naaman said. That's why he laid it out. If I give this fertilizer, there'll be a fixed value that would be observed. And if I give this fertilizer, there'll be another fixed value that will be observed. And if you're saying you don't believe that, then there won't be a value that be observed, the yield, there will be. How much crop I collect, that's going to be what that value is. Now you want to build up a scientific story for why it's that way rather than something else. That requires a whole other modeling structure. So you're basically a Bayesian, is that right? You got to be because you want to build a big model on the science. And I'm not opposed to doing that. But start with the potential outcomes as being the thing that you would observe. And then if you want to build other structure, you can. But that's going to certainly require something beyond randomization to do. So you're saying you don't like randomization inference either. You don't like Fisher randomization or Naaman or unbiased estimation. Is that right?
No. Okay, I guess if you want to push me a little bit, I think all this randomization is great at a group level because the group mean is stable, can be estimated and everything. So at a group level, everything looks beautiful. But to have a notation of observed eye and observed missing eye, that it's hard for me to think there is a value existence to be reviewed. At the group level, the mean of the group, treated and untreated, that is the actual approach to the limit, and that's clear, well defined. But the individual level, the not a counterfactual potential outcome of sub I at the time of assignment is hard to conceptualize.
Well, it's not the value isn't at the time of assignment, the value is going to be in the future, at a fixed time in the future.
But you already define it as if it is a single number.
Well, there will be something revealed, and that's what it is, whatever it is, right? So how to say this right? The idea is let's suppose, for example, I'm thinking of two possible economic interventions, two possible tax values and tax policies, and I wanted to estimate the median value of a house under each of the two tax policies. That's how do you estimate it? See, I think also you can choose the estimation of something with the with the estimand, because the median under one minus the median under the other, it's a little tricky. Yeah.
We're going to finish, but I
Okay.
invite people to stay and we have the room for a little while.
Fine.
Do you want to say something?
No, I'm done. Thanks very much.